Kepler's laws of motion. Kepler's laws of motion are of great historical importance because of what they initiated. Basically, Kepler took the astronomical data of the famous Danish astronomer Brahe and did the mathematics on that data to show these three laws. Now, we don't need to know the derivation of his mathematics, how these were shown. However, what it presented to scientists of the day, to Newton and Robert Hooke and Edmund Halley, and other mathematicians and scientists, was to come up with an explanation as to why it is the planets seem to behave in such a consistent, such a common way. It couldn't just be by accident. And really, this set scientists on the road to ultimately Newton's formulation of universal gravitation. Well, we can see here that the law of orbits, Kepler's first law, is a statement that the planets all move in elliptical orbits. So we'll talk a little bit more about how elliptical. But when you look at the data, the planets, again, the commonality here is the important theme. All of them seem to be in elliptical orbit around the sun. Now, one of the misconceptions I think students sometimes have about these elliptical orbits is the fact that in textbooks, the ellipse is often shown like this. It's very elliptical. They're exaggerating how elliptical the orbits actually are. So I think one nice thing, just as being someone who's studied physics and Kepler's laws, highlight in the actual elliptical orbit of the Earth. So we have the actual elliptical orbit of the Earth here, right? And the important thing is the eccentricity, 0.017. That is not much of an ellipse at all. To remind you about ellipses and circles, ellipses are described based on their eccentricity. And eccentricity is kind of just what the name implies, how eccentric. When something is eccentric, it's different. So how different is an ellipse from a circle? Well, if the eccentricity is equal to 0, that means the semi-major and the semi-minor axis are identical. B and A are identical. 1 minus 1 is 0. So for a circle, no eccentricity. Circles are not eccentric at all. So ellipses are eccentric, and the greater the eccentricity, the more drawn out, the more flat that ellipse is. So it's a misconception to think that the planets are in these wildly eccentric elliptical orbits. But they are all elliptical. The law of areas, a little more complicated mathematically. You do, however, need to know for the AP test, sometimes, again, a conceptual multiple choice question, is that the law of areas, the fact that when you look at the radius vector from the sun to a planet and consider any equal time period. So, for example, here I put in 10 days. You can put in whatever number of days you want into your notes. But just for example, 10 days and 10 days, that radius vector will sweep out equal areas in equal time. Kepler realized that's what the data was showing. And it turns out that that's a consequence of conservation of angular momentum. Again, we don't need the math behind it, but you just need to know that's a consequence of conservation of angular momentum, which I think kind of should make sense because you're sweeping out, right? There's constant angular momentum, as we've seen for satellites in orbit. So the final law, which was almost 10 years later, the law of periods, is something we have also really seen when we looked at geosynchronous satellites in particular. If we consider our circular motion satellite, and it works the same for the elliptical orbits, but if we're going to focus just on our circular motion equation, circular motion, mv squared on r, we've done this before, the only force is gravity pulling in, we lose the m's, we lose one of the r's, we get our equation that we've now done a number of times that V squared is capital G mass of Earth over r. We get speed equals distance over time, so we're going to plug that in for v. And if you take the period squared, just do the algebra, take the period squared divided by the radius cubed, you will get 4 pi squared over gm. Let's take a look at that. 4 constant, pi constant, capital G. Cavendish showed us that, constant. Mass of the Earth, constant. All of this is constant. So t squared divided by r cubed equals a constant, and it is the same constant, the same number, right? There's no difference here for any of the planets. 4 pi squared divided by capital G mass of Earth. It is the same value for all of the planets. So this is what set the scientists, the mathematicians down the road to trying to figure out what is going on, that there's this much commonality with what we are seeing happening up there in the heavens that needs to be explained. And ultimately, Newton gave us the answer, and Newton showed mathematically, if you take the force equation G, mass of Earth, mass of the object, and the little m here would be a planet, divided by the r squared for the planet. If you take that force equation, it will explain everything that Kepler was saying. Now, we're not going through the mathematical proof of that, but it is certainly of historical importance, so please make sure you copy down what you need to here in your notes, and we will continue on.